What's up, everybody? Here are the solutions for worksheet 13. We already went over these in tutorial, but I'll do it one more time. So for the first problem, we are given a graph of some function f, and we're asked to sketch the graph of g of x, which is defined as the integral from 0 to x of f of t dt. And we know by the fundamental theorem of calculus that this is an antiderivative of f, right? So the first thing to notice, if we are to sketch the graph of g, is that, first of all, g of 0 equals 0, because all I do is I take the integral from 0 to 0, and that's always going to be 0, right? If the upper and lower bounds of the integral are the same, then the integral equals 0. Now, one thing to notice is we know by the fundamental theorem that g prime of x equals f, so that means that the graph that we're looking at is actually the derivative of g. So the first things to look for is the zeros, and that happens at x equals 4 and x equals 8, so those will become the critical points of g. Now, critical points, that's 4 and 8, we can determine just by noticing that g goes from negative to positive here, and then from so g prime goes from negative to positive here, so the graph of g goes from decreasing to increasing, that's a min, and then from positive to negative here, so the graph of g has a max at 8, local max and local min. So another thing to notice, right, we also need the second derivative of g, and to figure out where the second derivative of g is 0, we look at the horizontal tangents on the first derivative. So that happens at approximately, let's say x equals 1, and at approximately x equals, I'll call this a 6. Okay? So now we're in good shape. So these are the critical points. The inflection points are going to be, like we just said, 1 and 6. And let's go ahead and try to graph this function g. So we're only interested in it from, actually I drew this wrong, let me redraw it. We're only interested in the graph between 0 and 10, so I'll go by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm marking the important values on my axes. Now I already said g of 0 is equal 0, so that's part of the graph, and now we can go ahead and continue plotting this. Notice that the derivative of g, which is f here, first is decreasing, so that means g has to decrease. However, in between 0 and 1, the slope here is negative, so the slope of the derivative, which means the second derivative is negative, which means we have concave down, right? Then we have concave up, and it's going to be concave up all throughout until it switches after the second inflection point 6 to concave down again, right? So if I want to draw something that's decreasing and concave down, that's going to look like this, and then it's going to change concavity at the inflection point 1, and it'll continue decreasing up until my local min of 4. So it should look something like this, and there's my local min. So it's not the best picture here, but roughly that's what it looks like. Then I continue being concave up now and increasing, right, positive.
So let's go ahead and do that. So increasing concave up all the way until 6, the inflection point. Then I switch again to concave down, but I continue to increase
up until 8. So we have this, that's the local max, and then with concave down again I start to decrease. Okay, so that would be the rough shape of G. Now notice I'm keeping it all below the x-axis here, and the reason for that is because remember G represents the area under the curve of F, and just to me, just kind of looking at the picture of F here, the area that's in this region seems a little bit larger than the area that's in this region, so I never get to have a positive net area from 0 to any x value here. Now for part B of this problem, what we have is a function which is the integral from 0 to x squared of f of t dt, and I'm asked to calculate the derivative of that. So d dx of the integral 0 to x squared f of t dt, and well, okay, the way we typically evaluate integrals, right, by the fundamental theorem of calculus, is I just pick f to be, capital F to be any antiderivative, so the whole integral should be capital F of t evaluated from 0 to x squared, right, that's by the fundamental theorem of calculus, and I just want to take the derivative of that. Okay, let's apply the fundamental theorem. So inside the parentheses what I'll have is capital F of x squared minus capital F of 0, and I want to take the derivative of this entire quantity with respect to x. Now f of 0, I have a function, I plug a number in, I get just the constant, and the derivative of that is 0, so I can ignore that term, which means all I'm looking at is the derivative with respect to x of f of x squared, right? And now we can apply the fundamental theorem together with chain rule to say that this is little f of x squared times the derivative of x squared, which is 2x. On the second page here, we have a similar problem, except now both the upper and lower bounds are variables. So we're looking at the derivative of the integral from x to sine squared of x of t squared over 1 plus 2 e to the t. I'll do the same technique, so I'll let capital F to be an antiderivative of this little f of t, and by the fundamental theorem of calculus, what the integral is going to be equal to is just, I'm not even going to rewrite it, is simply going to be capital F of top bound, so sine squared of x, minus capital F of the bottom bound, which is x. Okay, and I want to calculate the derivative of this with respect to x. So this is what I'm looking at. This is the expression that I'm looking at. I differentiate term by term, so I'm doing d dx of capital F of sine squared x minus d dx of capital F of x, and what that gives me is little f of sine squared x times the derivative of sine squared, which is 2 sine x cosine x, right? So actually I have a double chain rule here where the cosine comes for the second use of chain rule as the derivative of the sine, minus here simply little f of x. Okay, and now we can, since we have a formula for f here in the integrand, we can actually go ahead and plug in these values. So f of sine squared of x, that's going to become sine to the fourth, because I'm squaring twice, divided by 1 plus 2e to the sine squared of x times 2 sine x cosine x. So I just copy that part down, minus just f of x, right? So I copy that formula, except t becomes x now. So we have x squared over 1 plus 2 e to the x, and that is the derivative that I'm looking for. So quite a it's a pretty complicated formula there. Problem 3 has us just evaluate some antiderivatives, right? Just compute them. And for the first one, I just integrate term by term. So the integral of cosine, that's going to be sine. Integral of negative sine is going to be cosine. So I add cosine plus c. So that's that one. For this one, I have to apply power rule. So I add 1 to the exponent, which means I end up with x to the 1/4. But I have to divide by my new exponent a fourth, and dividing by a fourth is the same as multiplying by 4. So my answer is 4x to the quarter plus c. Next one up is another integral that comes from chain rule now. So the way to do this is you have to recognize that this 2x is the derivative of the exponent x squared here, right? So that means this must have come from the function e to the x squared plus some constant, and it does indeed work. When you take the derivative of e to the x squared, you get e to the x squared back, but you multiply by the derivative of x squared, which is 2x. So this is the way to do this particular integral. For the next one, I have integral of, let me write it a little bit bigger, 2x over x squared plus 1, and again the same technique is used. It's to recognize that this 2x on top, that is the derivative of the denominator x squared plus 1, which means I'm looking at the integral of a function 1 over something, right? And I know that's the natural log, so this should be natural log of x squared plus 1, and indeed when I take the derivative of that, I do get this extra 2x on top from chain rule, right? So that's the answer here. Whoops, I almost knocked over the camera here. Hopefully that wasn't too loud on the microphone. Okay, for the fourth problem on this one, again we have some integrals, except this time they are definite integrals, so we are actually going to get a number for them. Right, so the first one has me do the integral from 0 to 2 of this function. So I again integrate term by term using power rule. So for the first term, integral of x cubed is x to the 4th over 4. Integral of 6x is 3x squared, and integral of 1 is just x, and I'm evaluating this function between 0 and 2. So what I do first is I plug in the top bound. So it's 2 to the 4th over 4 plus 3 times 2 squared plus 2 minus, plug in the lower bound, so I actually end up just getting 0 for that, because these all have like an x in it. And when you do the computation, you end up with, I believe, 18. Now I have the integral from 0 to 1 of 1 over 1 plus x squared, and if you recall, it was on one of the previous exams to derive that the derivative of arctangent of x is 1 over 1 plus x squared. So the antiderivative here is arctangent, and I'm evaluating that between 0 and 1, so I'm looking at arctan of 1, top bound first, minus arctan of 0, and okay, arctan of 0 is 0, so this term we can ignore. The question is, what is arctangent of 1? So what we're really asking is, for what angle, let me draw it over here, for what angle theta do I have the tangent, which is y over x, equal to 1? And the answer to that is really simple. It is for theta equals to 45 degrees, right? Which corresponds, is the same as pi over 4. So the answer here is pi over 4 minus 0, or just pi over 4. Next integral. Before I integrate, I actually have to multiply things out here. So I'm looking then at the integral from 0 to 1 of 1 plus 2x squared plus x to the 4th dx, and I again integrate term by term. So this is x plus 2/3 x cubed plus 1/5 x to the 5th. And I'm evaluating this expression between 0 and 1. So when you plug in the top bound, you get some fractions here. You get what? You get 1 plus 2/3 plus 1/5, and when you plug in the bottom bound, you get 0. So adding these fractions together, I believe you get something like 28 over 15. For part D, the technique here is to rewrite the integral as integral from 0 to 4 of split the square root as a product. So square root of 2 times square root of t dt. Okay, and square root of 2 is just a constant, which means we can just bring it in front of the integral and do the regular integral of the square root of t function, right? So this should be, keep the square root of 2 in front. Antiderivative of square root of t is, well, I have t to the 3/2, but then I divide by 3/2, so I get 2/3. And I evaluate that between 0 and 4. So let's see what I get. When I plug in the top bound, I end up with, let's see, first I take the square root of 4, then I cube it, so I get 8. 8 times 2 is 16. I have 16 root 2 over 3. And then when I plug in 0, of course I get 0. So there's my answer. 16 square root of 2 over 3. For part E, I'm looking at the integral from 0 to pi of sine of theta d theta. So one antiderivative of sine of theta is negative cosine of theta, and I'm evaluating that between 0 and pi. What I'll do is I'll keep the negative sign in front. So now plug in the top bound, I get cosine of pi minus cosine of 0. So this is negative. Okay, cosine of pi is minus 1, cosine of 0 is 1, so I'm subtracting 1, which means that
for part F, the trick here is not to integrate. Of course you could do it, right? But to realize that this is what we call an odd function, which means its graph is going to look something like this, right? So if I do the integral from some negative x value to the positive of that x value, the areas here are going to be equal, symmetric, right? There's symmetry in the graph, so they'll cancel out, which means this whole integral is 0. Now lastly, I have integral from 1 to 2 of this expression, and just like we did in part C here, first I had to multiply everything out, so let's go ahead and do that. So I am looking at the integral from 1 to 2 of, let's see, I have x squared plus 2, x times 1 over x is just 1, so plus 2, plus 1 over x squared dx. Okay, let's take antiderivatives. This is x cubed over 3 plus 2x minus 1 over x, and I'm evaluating this between 1 and 2. So okay, we go ahead and plug in 2 first. That's going to be 8 over 3 plus 4 minus a half. Oops. Minus, plug in the bottom bound, so I just get 1/3 plus 2 minus 1. And if you do the computation here, I believe you get something like
29 over 6 if I did my algebra right. Okay, so that's our G right here. Now we have a couple more problems left. So for problem 5, we are given a function f. We don't know what the formula is, but we know what these integrals are. And the question is to compute the value of the integral from -1 to 5 of f of x dx. Of course, we have to use these three integrals, which means I have to break up this integral into pieces. So what I'll do first is I'll write it as the integral from -1 to, let's go to, I guess, -2. And then I can go from -2 to 2, and then from 2 to 5 using these two guys here. Okay, so I'll go from -2 to 2 plus 2 to 5 finally. So I was able to break it up into three integrals just like so. And now the question is, what are the values of these integrals? Well, I know from -2 to 2, that's 1, that's given right up here. So that's +1. I know that from 2 to 5, that's a 2. So I add 2. So I know these two guys, these are taken care of. What about this one? I'm looking at the integral from -1 to -2. However, I'm only given the integral from -2 to -1, so the bounds are reversed. But we know that one of the properties of the integral is that if I have the integral from a to b of some function, that is the same as the negative of the integral from b to a. So when I flip the bounds, I simply have to add a negative sign for the value of the integral. So now I should have just -3. So that means, add all of these together, I get 0. For problem 6, we are given a function that is integrable, and I should have mentioned continuous, that satisfies integral from 2 to 7 of its absolute value. Right, so I have integral from 2 to 7, absolute value of f of x dx 0. So I know for sure that this is true. Now, what can we say about the value of the integral? What's going to happen is, and I don't really have enough room to explain it here, but what's going to happen is that if I take just the regular integral from 2 to 7 of f of x dx, I'm going to get 0 again, right? And for problem 7, the concept is similar, right? And so what's really going on here is, okay, the absolute value of f, that's always greater than or equal to 0, right? So I know that if I integrate this, then the integral of the absolute value of f is greater than or equal to 0. That's one of the properties of the integral. Equality only happens when f is, okay, at least for the purposes of this class, when f is the constant 0 function. So the integral of absolute value of f equals 0 precisely when the absolute value of whatever is inside here, as long as the function is positive, then this is 0, right? And of course the absolute value of a number, so maybe I should write it like this: f of x for all x between 2 and 7. Okay, but the absolute value of a number, right? So I take x, I plug into here, the absolute value of that is 0 precisely when that number, right? So whatever's inside the absolute value is 0. So the integral of f is just the integral of 0 between 2 and 7, and that's exactly 0. So that's kind of the reasoning behind this. Now problem 7 has a similar concept, right? I'm looking at the integral from 0 to 1 of the square of a function, and I do a similar thing, right? So notice that if I take a function and I square it, right, and by which I mean I just multiply it to itself, I don't mean composition twice, this is greater than or equal to 0, so that means that the integral of the square is greater than or positive
or non-negative. The area should be positive. But what does that mean, right? If this is 0, then equality only happens, so this thing is 0 only if whatever's inside is 0, right? And again, that's not quite true, but if the function is continuous and integrable, that is true. So what do we have? The square of something is 0, but then that something has to be 0, right? So again, just like in the previous part, when I integrate from 0 to 1 my function, that's just the integral from 0 to 1 of 0, which is 0. Okay, so in both of these cases, what I'm doing to my function is I'm making sure that it's positive, taking integral over some region of that. If I get 0, then the integral of the original function without absolute value and without the square has to be 0. Right? And that's it for this worksheet.